So now we will move on to discuss the multi-phase flow equations. Up till now, we focused only on the single phase equation for fluid flow in porous medium, right? This is the dy or the dx. This is what we focused on before, right? We just ignored this temporarily, but we know flow potential controls the flow, right? And it's dx. So this is your flow potential, which is basically the pdx minus rho g. D is depth. This capital letter D is depth, and how it changes with respect to x in the x direction. So if your grid is perfectly horizontal, so although I'm already drawing multiple grids, what I should have done is this, right? So this is x direction and it's perfectly horizontal. Then going in this direction, the depth is constant, right? Depth never changes. So the ddx will always be 0. But it's important to note, if this were to be the case, and now x direction is dipping, then of course you already know there is a change in depth, right? So flow potential will contribute, even though it's 1D. It's 1D, but the x direction is dipping. So there is a change in depth with respect to x direction. And it's precisely this height, y2 minus y1 divided by x2 minus x1. So there is a slope there, and gravity effect will play a role. Good. Right hand side remains the story term. Again, flux term on the right, story term on the right. Sorry, flux term on the left. This is flux, right? Because this is U, which is flux, and this is storage or accumulation term on the right. Talked about this before. So you should be able to write this equation from memory. Now, we want to move to multiphase. And it's as simple as writing out this equation for each phase. Many times people use phase alpha to represent oil, water, or gas. But here we are writing it out. So O representing oil, W representing water, and G representing gas. So first off, we will have pressure in different phase alpha. So you have pressure in phase alpha, which could be oil, density in phase alpha, viscosity of phase alpha, because there is a different density, there's a different viscosity for oil than for gas than for water. So all these terms, density, viscosity, will have their respective phases. What do you do to permeability when you have multiple fluids? We talked about that before. So now you will have the measure of the ease of flow of a phase in the rock in the presence of other phases, and that introduces the concept of what? Relative permeability. Because relative permeability, to say phase alpha is permeability of phase alpha divided by the absolute permeability. So K of a phase alpha, the relative permeability of a fluid alpha in the presence of other fluids, will be KKR alpha. So if alpha is oil, KO, which is oil permeability, will be permeability, absolute permeability of the rock, multiplied by the relative permeability of oil. relative permeability is usually written as a function of saturations, right? So for oil and for water, it's written as a function of SW. So I mentioned two concepts come to bear when we talk about multiple phases, and those are relative permeabilities and which other concept? Capillary pressure. Because now we've discussed pressure in different phases, right? Pressure in phase alpha. So we need to be able to relate the different pressures in the phases. So capillary pressure does that. So capillary pressure for oil, water, for instance, will be P in the non-wetting phase minus P in the wetting phase. Always capillary pressure is defined as the pressure in the non-wetting phase minus the pressure in the wetting phase. So for PCGO, gas will be the non-wetting phase, so it's going to be PG minus PO. And so all these P's will either be PG, PO, or PW. So let's write this equation out for single phase oil. No, for oil in the presence of other phases. It's already written out here, but I want to do it from scratch so that you can see how we actually got this. So I'm going to do it on the right hand side here, starting from about here. So I need some space. Good. So it's d dx of rho, well, density of what phase? Oil. It's no more just kx because you have multiple fluids. So we need to use effective permeability, which is k naught, right? And k naught, by definition, is kKRO. So effective permeability to oil is absolute permeability times relative permeability to oil. So that's going to be KRO, which is what you see here. Kx telling you it's permeability in the x direction because we're looking at 1D equation. So that's divided by what viscosity? Is it viscosity of water? No, it's viscosity of oil. And then pressure in what phase? In the oil phase, because we're writing out this equation for the oil phase. Density of what? The oil phase. And the dx equals what? Looks like I can pull it a little bit to the side. No, I can't. Well, equals what? For now, I'm just going to write it on this side. D dt of what? Phi, which never changes. It's just porosity and density and what phase? Oil phase. So that's what you have. But if you look at this equation, BO is here. We don't see densities anymore. Instead of densities, we see formation volume factor. So how did we move from here to here? Well, what's the definition of BO? Oil formation volume factor. Oil formation volume factor. If you forget the definition, do you remember the units? The unit is what? Reservoir barrels per STB. So the definition is volume at reservoir conditions divided by volume at standard conditions. But this is densities. What's the equation for density? Density is mass per unit volume. So it's inversely proportional to volumes. So BO is basically rho SC divided by rho V. I mean rho at reservoir conditions. You see that? And rho at reservoir condition is just rho. Why? Because this is mass, which never changes per unit. I mean, the mass does not change regardless of the conditions. Meaning, regardless of the pressure and temperature conditions, the mass of the fluid is constant. What changes is the volume. So mass divided by volume at standard conditions divided by mass divided by volume at reservoir conditions. Again, mass does not change, so those masses cancel, and VR goes up, Vs comes down because this is 1 over VR, this is 1 over Vs divided by 1 over VR. So VR goes up, Vs comes down. And that's exactly what this is. So this is the expression for BO as a function of densities. So this is density of oil at standard conditions divided by density of oil at reservoir conditions. Obviously, these equations are all at reservoir conditions. So you can write it out as rho, or just forget about the rho O and just say rho SC. We already know it's density of oil at standard conditions divided by density of oil. So how do we introduce BO into this equation? Very easy. Divide through by rho SC. Right? So if you divide every term here by rho SC, this becomes rho O divided by rho SC, density of oil at standard conditions. This one becomes rho divided by rho SC. You can put it inside the parentheses, you can put it outside. Why? Because density of oil at standard conditions never changes. Because we specify standard conditions. And what standard conditions? 14.6, 14.75, whatever you use, 14.7 roughly, PSI, and 60 degree Fahrenheit. So that's standard conditions. So the density of the oil at standard condition is constant. So it can go into the parentheses, it can go outside, the same deal. And now you have rho over SC. Do you divide this other one also by rho SC? That's a question for you. Think about it. Are you going to divide that term also by rho SC? No. Why? Because rho SC is already showing up here. So technically all we did was to take this out, to divide this by rho SC. And if you do that, it's equivalent to taking that into the parentheses. Which is multiplying both this term and this term, so you don't divide this again by rho SC. Good. So what's rho of oil divided by rho SC? Is going to be 1 over BO, right? Inverse of this is rho over rho SC. So everywhere you have rho over rho SC, substitute 1 over BO. So the equation finally becomes, I'm going to write this one first, the flux term first. So d dx 1 over BO, right? So we can write kx kRO over mu O, then BO. That's the 1 over B naught. And then everything continues as before. Equals what? Phi over BO. Are we done? No. Remember, this is the storage term, right? For single phase flow, only one fluid in the porous medium. But for multiple phases in the porous medium, well, the volume of the oil in the rock is not going to fill up all of the porous, all of the pore volume. It's going to be you're going to have oil, water, and gas in the pore volume. So to capture the fraction of the porous volume, the fraction of the pore volume that is filled by oil, you're going to need to multiply this by S, which is the saturation of that phase. So what I'd written before will be d dt of phi rho S of that phase alpha. In this case, alpha is oil, so phi rho S naught. And then we divided that by rho SC, this phi of the density of oil. And what does that give you? Here is phi over B naught times saturation of oil. So that's why saturation of oil shows up, because again, the pore spaces, which is this, the white regions, right, will be filled by oil, water, and gas. So saturation of oil is the volume of that oil divided by the total pore volume, right? Saturation of gas, same deal, right? And saturation of water will be volume of water divided by the pore volume, so that when you add up all three, they will add up to 1, because VO plus VG plus VW is the total pore volume. So the sum of all those saturations will be pore volume over pore volume, which will be 1. Do you see that? Because it's VO over VP plus VG over VP, all right, plus VW over VP. And we already said sum of all three is VP divided by VP 1, which is one of the constraints we will see on the next slide.